So this is the second lecture in our course. A last set of videos we talked about sets. So that was taken from chapter 1.1 to 1.3. Now sets are mathematical objects, and essentially they're just collections of things. We call those things elements, and we got into some of the basics of sets and set theory, and all of those things are going to be useful for us when we talk about today's topic. So today's topic is something that's called probability. Now, once again, it's going to be drawn from chapters 1.1 to 1.3, and by the end of this lecture, we will have covered everything in up to 1.3. What is probability? And so probability is a number that's assigned to an event that tells you how likely it is that the event will occur. So it tells us how likely it is the event will occur or happen. Okay. So if we say that A is our event, we are going to use this notation, P of A, to talk about the probability of event A. Now, essentially, this P of whatever notation is kind of like a function, and the probability function is going to have some special rules attached to it. As a standard definition, we are always going to assume that the probability of any event is going to be a number between 0 and 1. If an event has a probability equal to 0, that means the event will never occur. If the probability of an event has a probability of 1, that means the event will always occur. So these two situations are the only situations where there's certainty. 0 means it will never happen, it's certain. 1 means it will always happen, it's certain. If the probability of A is closer to 0, that means it's something that is less likely to occur. If the probability of A is closer to 1, it means it's more likely. And now you say, well, how can an event have something that's less than 0 or 1? Doesn't the event happen or not happen? And that's where we start getting into ways of calculating probabilities. And so the idea here is that probability is going to depend very much on repeated trials of an experiment. And so we need ways to assign probabilities, and now we start delving a little bit deeper into what those numbers mean. So how do we assign these probabilities? Turns out there are a lot of ways of doing things, but we are going to focus on two. The first one is what we'll call the classical probability. So this is where you have an experiment with equally likely outcomes. Usually this happens when you talk about really simple experiments in things that we call games of chance. Flipping a coin, rolling a die, drawing a card from a standard deck of cards. We are going to define the probability of event A as the number of desired outcomes over the number of total, or the total number of outcomes. And the notation that I'm going to use is N of A, so the number of outcomes in event A, and capital N will stand for the total number of outcomes. So this classical definition works when your sample space is pretty straightforward. So for example, if you flip a coin, the sample space is heads or tails. And here N would be 2. You have 2 outcomes happening. If you want to know the probability of getting tails, well, you have to figure out how many outcomes in your sample space will get you to tails. Well, there's only one of them. And by the definition, that one outcome gets divided by the number of total outcomes here, and it's 2. So the probability of getting tails is 1/2. Now, there's a link to a sheet in this video link, and let's say we're interested in the probability of getting the sum of 8 when we roll 2 6-sided dice. And so on this sheet, you'll have all of the outcomes available and all the different possibilities. But what you'll find is that when you roll 2 dice, there are 36 possibilities in terms of the outcomes. And if you're interested in all of those that have a sum of 8, you can see very clearly from the sheet that there are 5. So the probability of getting a sum of 8 on 2 dice is 5/36. So life is really good when you're in this simple situation, but many things don't fall in this simple situation. So things where you do experiments or asking questions, what's the probability that somebody's going to get a heart attack by the time they're 50? Well, it's not equally likely that they'll get a heart attack versus not. So we need to slightly modify the definition to consider these other cases. So this is what's called the empirical or frequency definition. Here, you're assuming that you've got a repeatable experiment, which again, you can poke some holes in, right? I can't repeat me getting a heart attack by 50 all over and over and over again. And here, you don't necessarily need to have repeatable outcomes. Okay? So the true definition is going to be taken as the limit as the number of repeats of our experiment goes to infinity, and we're going to talk about the number of outcomes that we want over the total number of outcomes. Now, I'll call this the true definition, but usually we are okay with working in the approximate situation where we essentially just drop the limits. You might say, oh, limit, I have to do all that stuff from Calc 1, limit laws, etc. None of that. So the probability that you're typically going to work with when you have an experiment is just the number of desired over the total number of outcomes. So what do I mean by that in this situation? Let's say you poll 135 people and you ask how many of them like the Canucks. And let's say 85 of them like the Canucks. So the probability that a random person might like the Canucks, the best thing you can say is, well, it'll be 85 over 135. So it's very simple to calculate. Now, in situations where both the classical and the frequency definition apply, there's a connection between them. So in situations where both apply, what has to happen is that as you take the limit where n goes to infinity of this probability definition, this has to get to the true classical definition. So the frequency approximation has to get closer to the true classical. So what that means is kind of like saying, if I were to roll 2 dice 100 times, and let's say out of the 100 times I got 12 out of 100 in terms for summing them up to 8. If I were to do it 200 times, maybe I would get, 19 out of 200. So every time I do the experiment, I get a slightly different number. But the point here is that as you keep going with a larger and larger number of trials, that value is going to eventually have to approach the 5 out of 36 that the classical definition tells us has to be the case. So these two definitions are going to be the way that we go about calculating things. And the last thing that I'm going to mention here is a set of rules called probability-axioms that are going to help us perform calculations for more involved probability problems. Okay, so in this case, we're assuming we've got some sample space, some experiment that generates these outcomes. We're going to call these outcomes A1, A2, all the way down to AN. We're assuming that these events are there, and there's a set of rules that these are going to have to follow. Now, we already know that probability has to be a number between 0 and 1. So the first axiom here says that all of your individual probability values have to be bigger than 0. And that's for all I equals 1 to n. The second one says that if you've got your sample space, we're going to write this thing down. The probability function applied to the sample space has to give 1. Some outcome must occur. The third one is going to be the useful one for us, and this is going to be the one that we get to use in a lot of calculations. So if it happens to be the case that our events, A1, A2, all the way up to AN, are what we call exclusive. So we talked about this last time. Exclusive means they can't happen at the same time. Another word for it is going to be disjoint. Then this mathematical rule will apply, that if you are ever to take the probability of the union of these outcomes, you will be able to essentially distribute that probability function to each one of those events individually, and then use your knowledge of the probability of those events. And that one is by far the one we're going to get the most mileage out of. Sometimes we abbreviate it with sigma notation, and we get to this result. So this last probability axiom is really the one we go ahead and use in our further calculations. So remember that an axiom is just a set of rules that we're all accepting as true and is that we're all agreeing upon as the starting point for how we go further. So in the next video, we're going to start learning about some rules based on these axioms, and that will help us problem solve in more complicated situations.